All right, so kind of where we're going. So we'll pick up that last regression or Excel example we're looking at. We'll finish that. I'll probably start doing a little bit of exam review today, and then we'll kind of review for the exam on Friday as well. Won't be. I think originally I had said that we were meeting next week on Monday to do some more review. We won't be meeting anymore. I think we should be pretty good with review today. On Friday, I'll also post the videos from my other sections and make sure I'm kind of covering kind of some different questions. So you should have every single question of those practice exams worked through. Now I gave you the answer keys and some detailed answer keys on the one. So those should be pretty adequate, but you also have those videos that kind of go back and look to see if you're getting stuck on anyone, how to kind of work through it. What else? Oh, I also kind of got updated on Canvas your iClicker grades. So you can still see all your old grades, but right, they're not kind of counting towards your grade now. Here, I kind of put up what your iClicker score is with the 3 lowest drop, right? So this will be kind of your end kind of iClicker score. That'll be the one that gets factored in. So you now have, you know, at least one thing finalized. Once we get kind of past this week, those Excel and that last connect, if you want to do them, I'll kind of get your grade reflected with the lowest drop there as well. Prior to I should be able to get that done over the weekend. For the exam itself, it'll be 2 hours long. So usually we have an hour to 20 questions, 2 hours be 40, but I'm going to cut it to make it only 30, right? So just time shouldn't be an issue. It'll primarily be kind of the second half of it. I think maybe in the syllabus original, I was thinking of doing a comprehensive exam, but I think I'm going to take it easy on you guys and just do what we've done since the last exam, right? So all we're going to do are 2 population examples, right? We're looking at sample differences and then linear regression. So it's going to be about half and half, right? Maybe a little bit less than half of linear regression, right? But pretty close, okay? So the practice exams are not reflective of like the length of the actual exam, but it's all information that could be asked, right? And as we work through them, I'll kind of add in some additional questions as well, okay? So, unless there's any questions for me before we get going, we'll kind of jump back to what we were looking at last class. So, we kind of had this example where we were trying to identify kind of whether or not there was any racial discrimination going on kind of at issuing tickets, right? And so we said, if we include all these different indicator variables that kind of have the race driver combination, and we leave out the group of white driver, white officer, then the interpretation of our coefficients would be if I go from the 0 to the 1 group, so go from when the officer and driver are both white, when the officer is white and the driver is non-white, what's the change in my predicted Y value? Well, here, if my Y value is to 1, 0, we said the units were kind of what? Close probabilities, right? So here was the change in the probability. We go from not getting a ticket to getting a ticket, right? So when we looked at the output, we said on all, these different kind of driver officer race combinations, they were all positive. So relative to when the driver and officer were both white, all of these other scenarios, there's actually an increase in the probability a ticket was issued, right? Holding constant, the driver's age and officer's years of service. So that was kind of where we left off, right? And we said, well, look, not only do we find evidence that there's some, possible discrimination going on, right? These probabilities for when the officer and driver aren't both white are higher, right? We can also say that they have a significant relationship, right, with that Y variable. So remember, we always start out assuming that these slopes are equal to 0. The only way we can reject that is if our p-value is less than alpha. So the only way we can say that this variable has a significant impact on my Y variable is if that p-value is less than alpha. So it doesn't matter what alpha we want to choose here, either the negative, these p-values are basically 0, we can reject the null for every single variable that we've included here, right? All of these p-values are basically 0. We can say that each one of these has a significant relationship on the probability of whether or not you get a ticket, right? That Y variable. Now I can interpret these that way, but I also need to be cautious, right? So like, for instance, relative to when the officer and driver are both white, If the officer's white and the driver's non-white, the probability that the ticket is issued goes up by 0.067 or 6.7% increase. Right? We're kind of going back and forth between probabilities and percentages. So I can interpret that, and I can make that interpretation. Say I can reject the null, but why should maybe I be a little bit cautious with these results? Yeah, if I look at that R squared, remember, what does the R squared tell me? It tells me how much of the variation in my Y variable I'm explaining with all of these X variables, right? Another way to think about it is, how much of my Y variable can I explain with these X variables? More technical is like how much variation in that Y variable am I explaining when I'm using these variables to make my predictions. Okay? So 0.03, right, as a proportion I'm explaining, means I'm only explaining about 3%. So there's still 97% that I can't explain, which means there's probably a lot of important omitted variables, which we said if we have some important omitted variables, our coefficients will kind of have some bias built in. The more control variables that we add, the closer we get that R squared to 1, we're eliminating more and more of that bias. So if I had additional data here, I want to try to include it. In fact, just to kind of get a little bit of a taste of how we're doing this in Excel. So I'm gonna, there we go. Maybe. Well, I'm gonna redo this. So traffic stop data. So this is up on Canvas. It's a little bit bigger of a file, so it might take a second to open up. But I just wanted to kind of go through Excel, one more example of how we run these regressions. So I start out, and I have slightly different variables than the one I was kind of using in on the slides, but that's okay. We've got some kind of measure of, is the officer, the driver white, officer, driver, both white, right? I also have whether or not a ticket was issued, whether or not there was an arrest made, driver's age, all these other things. So one thing I think I started to mention last class was when you run these regressions in Excel, anytime you want to include a set of X variables, they all have to be right next to each other, right? So maybe I want to include not just driver's age, but was the driver male or not? So I'm just going to move these columns over. And also, instead of just the officer's years of service, I'll include whether or not the officer was a male or not as well. Drag this over here. Now, I go to my data tab. I should have that data analysis added in. Remember, that's just files, options, add-ins, manager add-ins. If you go on a Mac, you should just go to that tools bar at the very top. Go to Excel add-ins down towards the bottom. Make sure the analysis tool pack is selected, and that data analysis tab will be under the, data analysis option will be under the data tab. Okay? So I hit data analysis. I go down to regression, hit OK. My Y variable, I want to try to predict whether or not they're going to get a ticket. So I Control Shift or Command Shift on a Mac, hit the down arrow. I then want to select my X variables. I put them all next to each other now. I'll select all of those X variables, Control Shift, Command Shift on a Mac, hit the down arrow. I selected my labels, put it on a new worksheet, hit OK. Now I've got my output here, right? Oops, I don't want to put a filter. I wanted to zoom in so we can see what I'm doing, okay? So here I've got kind of my different variables, their associated coefficients, and their standard errors, test statistics, and p-values. So if I was trying to kind of, well, what's some other things that we might be expected to do? And I'll do it in Excel here, but I'll also show you some examples where, we're working through this by hand. So I'm going to delete these columns just to kind of make it so I can have everything on one line. So anytime we want to make predictions, all we're really doing is saying, okay, look, if I want to say predict tickets, and I've got, I don't know, driver's age, years of service, and then all these other variables, right? Once I run this regression, I now have the values for my intercept and all of my slope coefficients. So I'm just going to start plugging those in, right? So it's like 0.473, driver's age is what? Negative 0.002, years of service, 0.009. I'm just going to start plugging in these values where they go, right? Those different coefficient values. Now, for a hypothetical driver who's 30 years old, officer's years of service is 12, I can start plugging in this hypothetical person's values into my X variables. So really all this becomes, in order to make predictions of our Y variable, take each coefficient, each variable's coefficient, multiply by the hypothetical value for that person, for that specific variable. Add to that the next coefficient times the hypothetical person's value for that X variable, so on and so forth. And then don't forget the intercept. So, excuse me, let's think about a hypothetical person. So we're always going to put a 1 here just so that we get the intercept added in. Anything times 1 is itself, so that'll be nice. Let's say that the driver was white, officer was non-white, which means this would be a 0 as well, right? This is only a 1 if both the officer and driver were white. Say the driver was male, 35 years old. The officer was a female, so this would be 0, right? And then officer's years of service, we'll do 12. So what we're then going to do is say, take each variable's coefficient and multiply it by this hypothetical person's X value, right? Or the value for that X variable. So notice here for the intercept, I'm just multiplying that by 1 to make sure it gets added in. But then when I copy this down for here, right, it takes the effective 1 year of age, multiplies it by what age that person is, 35. So that's what's going to be getting added into our prediction. So I now have every variable's coefficient times the hypothetical value for X. Now it's just a matter of adding all those up. Right? I've got all my coefficients plugged in, got my hypothetical X values. It's a matter of adding those up, right? So I get this person's predicted probability of getting a ticket would be about 0.53, right? Based off of all this information. Okay. Any questions on that? Okay. Oh, I know what I was going to say. There's one more thing I want to mention. So, what if I want to say which of these variables can I say has a significant relationship with whether or not you get a ticket, our Y or our dependent variable? Which of them have a significant relationship or effect on that Y variable at the 5% significance level or 95% confidence level? So my alpha there, 0.05. So the variables that I can say do have a relationship would be the ones that I could reject the null for, right? Because the null is that there is no relationship. So I'm going through and saying, okay, I can say there's a significant relationship if I can reject this null. The only way I can reject the null is when my p-value is less than that alpha of 0.05. So I go through all of my variables. This is 0, 0, 0, 0, pretty much 0. Everything has a p-value that's going to be almost 0, so that's less than 0.05, except for whether or not the driver is male, right? It appears that the gender of the driver does not have a significant relationship at that 95% confidence level or at the 5% significance level. Now it's really close, but right, just on the other side of it. Questions on that before we keep moving? Yeah.
So just to verify, so if you can't reject it, then it does like affect it.
Yeah, so if you reject the null, you're saying it does affect that Y variable, or it does have a significant relationship. Yep. Questions? We're keeping moving here. Oh, I think I had one more set of results just to kind of make it interesting. Don't worry about this. If I change that Y variable to whether or not they got arrested, so it looks like there was maybe some discrimination going on at issuing tickets. When it comes to whether or not you get arrested, it does look like, you know, there is an effect here. They're a lot smaller, right? But also, if I look at these p-values, even at that last kind of benchmark, 90%, my alphas here are all much larger than alpha 0.1, right? So I actually can't reject the null. So I can't say that any of these different officer driver race combinations, if there's really any difference in the probability of getting arrested at that stuff, right? So we found evidence that there's some discrimination going on in the issuing of tickets. Didn't find strong evidence that there's discrimination going on when it comes to getting arrested at a traffic stop. I'm guessing that's explained by a whole thing about, you know, like previous arrests, did you have a warrant out, things like that. Oh, once again, also, we should be, that isn't an end all be all, doesn't mean that there isn't discrimination going on, because RR squared, 0.002, the portion of variation in whether or not you get arrested at a traffic stop, we're only explaining about 0.002 of it, right, or 0.2%. So there's still a lot of the 99.8% that we can't explain, with not using just these 5 variables, right? There's 99.8% we can't explain. Question. Okay. I think that's all I want to say. This is kind of just a summary. Of some of the findings. We're not gonna like quiz you or test you on those, but just kind of an interesting example. Kind of shows the power of what you can do. Start to identify things like discrimination. But we'll go through. We'll kind of start doing some exam review. All the exam review stuff I'll kind of do up here on the dot cam, so it'll be recorded, so you can always go back to it. I will start with, unless there's going to be a strong opposition, just working through another regression example here. Is everybody okay with that? Kind of make today a little bit more regression heavy, and then we'll kind of go back to some of the older stuff afterwards, and then kind of during next class as well. So actually, let's go to practice exam B. I did A with my other sections, so you can kind of have both of those up there. So if we have practice exam B, I'm going to scroll down to, and that's actually very similar. It's probably just different. I'm asking about different variables. So I've got this kind of set up where I've got some regression output, and I am wanting my dependent variable of wage, which is measured as dollars per hour, right? So my dependent variable I'm trying to predict is going to be someone's hourly wage, and I'm using these 4 variables, right? So I've got education, years of education, years of experience, someone's age, and then this gender variable, which is a 1 if they're male, 0 if not, right? So I run this regression. What is it going to look like if I was just going to write out what that regression would look like? Well, I'm trying to predict wage, right? So that's my Y, or my dependent variable. I'm going to have some intercept value. I had education. I had experience. I had the person's age. And then I had this variable. And here I wrote it as gender, but just to make it easier, it was a 1 if the individual was male, 0 if not. So this is my regression equation. I had these 4 variables in the dependent variable in the data set somewhere. I ran it. I obtain all these coefficients, right? So all I do is I go to these coefficients, right? And I can start to think about, I'm just going to write them in and I'll show you. I could plug all of these values in to my slope and my intercept coefficients in, just so I'm getting all those numbers right? Just plug it into my regression equation, right? Now I can kind of come up with some hypothetical person. I could predict what their wage is going to be, right? So we said the way that we interpret these coefficients, right, is always going to be a 1 unit change in the X variable causes the Y value, the Y variable to go up by whatever that coefficient is, okay? So if I were to say, have 1 more year of education, that would increase my predicted, you can think about it this way, if years of education was 10, then I would be adding in 10 times 1.233. If it's 11, I'd be adding in 11 times 1.233. So going up by 1 unit, that increased my predicted Y by whatever that coefficient value is. So the way we interpret these coefficients is a 1 unit change in our X variable, so 1 more year of education, would predict that the hourly wage from our data set we're looking at goes up by $1.23. Any questions on that? How would I interpret kind of the age variable? So what would a 1 unit change in age be? Being 1 year older would predict here that your hourly wage actually goes down by about $0.019. Now I think if I remember, this is like restaurant data, so it kind of makes sense. Like your physical ability probably matters to some degree. So getting older, by actually decreases kind of predicted hourly wage. And remember, it's holding everything else constant. So it's two people with the same education, same years of experience. They're either both male or they're both female. One of them is 1 year older. We would predict their hourly wages 0.019 cents, or sorry, $0.019 lower, about 2 cents lower. Just as a reminder, how would I interpret variables that I have that are just 1, 0? So how would I interpret this male variable? So it's a 1 unit change in that X variable if it's just 1, 0. We're doing,
You're a male, you make that as one.
yeah, so it's always, if you're comparing that one group to the 0 group, so you can say it a couple different ways. A male relative to a female, we would expect the predicted hourly wage to be about $2.29 higher. Right? So once again, this would be maybe evidence that there may be some discrimination going on here, right? In pay, wherever the sector this was at, right? And so I can also kind of think about it as like, it's always relative to the base group. So going from the 0 to the 1, right? If I'm looking at a male compared to a female, right? Going from looking at a female to a male, I would predict that the wage was about $2.29 higher. Okay? So that 1 unit change, if it's a 1, 0 variable, is just going from the 0 to the 1 group, right? This is like when we did the student athlete one, right? The impact on GPA, going from not being a student athlete to being a student athlete, right? Going from the 0 to the 1 group, that would be the predicted change in our Y variable. Yeah. Other questions on this? So we could come up with like a hypothetical person. Actually, before I do that, what would the effect be of being not just 1 year older, but 10 years older? How would I find that? Yeah, I just take the coefficient, the effect of 1 unit, 1 more year, and multiply it by whatever increase I'm interested in. Here I said 10 years old, right? You're just scaling it. Now let's say I wanted to make a prediction for somebody who had 12 years of education, 4 years of experience, they were 30 years old, and female, right? So that would be a 0. All I do, I've got my coefficients plugged in. I just plug in those hypothetical values for X. Now it's just a long equation, right? So this would be like, don't forget the intercept, right? And then 1.233 times 12 plus 0.417 times, 4. See if I can get this on. There we go. Plus, actually, this was negative, so minus 0.019 times 30. And then here, I don't really have to do anything because I'm multiplying by 0. Right? Questions on that idea? So this is something I might ask you how to do on the exam, is to make a prediction, right? Any questions on that before we keep moving? Okay, so I asked you here to interpret the coefficient on one of these variables. I could ask you on any of them, right? We kind of talked about some of the other ones. Before we go to question 11 here, I also could ask you the following, right? So how would I interpret the intercept here? So how would I interpret my intercept coefficient? So remember, the way we interpret this intercept coefficient is if every single X variable were equal to 0, 0 times anything plus 0 times anything, that's all going to go away, right? Anything times 0 is 0. So when all of our X variables are equal to 0, the intercept is our predicted Y value. Right? So the way that we always interpret this intercept is it's the predicted Y value when all of our X variables are equal to 0. Might be a good thing to know. So when all the X variables, so someone with 0 years of education, 0 years of experience, their age is 0 and they're female, we would predict their wage would be $8.68. This interpretation will be weird, right? You can't see someone who's 0 years old. We said a lot of the times this intercept is just like, it's just a starting point. We may never actually see it in practice, but a line has to start somewhere. Now with 4 variables, it's not a line, well, it's like a 4-dimensional line that we can't really envision, but there is a starting point, right? So that way we always interpret that intercept is when all of our X variables are equal to 0, the intercept is our predicted Y value. Okay. Questions on that idea? Okay. Okay, so the next one, this should hopefully be like really easy points on the exam. I'm trying to give you some really easy points when I ask you the next question. So what is the test statistic for the age coefficient here? Right? Let's just get this all in one line, right? Actually, yeah, we could do this for any of the other variables, but let's say, what's the test statistic? I left it off here for that age variable. Well, if we go to the formula sheet, that's up there on Canvas, right? And we'll kind of talk about some of this in a second. I'm reminded that my test statistic equation is simply take that coefficient and divide it by the standard error. So if I'm looking here at my age variable, all I'm going to do is take that negative 0.019 and divide it by that associated standard error of 0.083, right? It's as simple as this, all right? So these test statistics for coefficients should be very easy points, right? You just take whatever that coefficient estimate is, you divide it by the standard error. Okay? Any questions on this? Also, standard error, kind of remember this is like, so our standard error, another way to think about it is it's kind of like the, standard deviation of those coefficients. So standard deviations will always be positive. Standard errors are always positive. So the sign of your coefficient tells you the sign of your test statistic. So here I had a negative coefficient. So I know automatically my test statistic should be negative. So right away I can rule out C and D, right? From there, it's a matter of getting this entered in my calculator. I believe it's like 0.22, or was it negative 0.229, right? So these test statistic ones should be really easy, okay? Any questions on that before we keep moving? Okay. I didn't ask these questions, but these are ones that'll be fair game. So talked about test statistics. What percent of the variation can I explain using just these four variables when it comes to the variation that exists in our y variable of hourly rate? The proportion that I can explain would be what? Just my r squared, right? So I can explain the proportion of 0.368 or about 36.8%. So there's still about 60% I can explain. So we'll be a little cautious with these results. Remember, they're just providing evidence of a correlation. There's still 60% that we need other variables to be able to explain. So a little bit cautious. What would happen if I then went out, I got some additional data, I included like, I don't know what sector they were working in, or maybe what company they were working in, what state they were working in, some additional controls, what should happen to my R squared? Yeah, if I just have more information, I'm able to make more accurate predictions, my R squared should increase, right? I should be able to explain a higher proportion. Which of these variables at the 90% significance level, 90% confidence or 10% significance level, which of these variables can I say has a significant relationship with hourly wage? So remember, how can I say that they have a significant relationship? Well, we start out assuming that the slope is equal to 0, that there is no relationship. So the only way I can say that there is a relationship is if I can reject that. How can I reject that? If the p-value associated with that coefficient estimate is less than this alpha, and I think I said of 0.1. Okay. So really all we're going to go through and do is which of these variables have a p-value less than 0.1. If they have a p-value less than 0.1, those are the variables I can say have a significant effect on that y variable of hourly wage. So the intercept shows up as significant. The education goes up, right? 0.002 is less than 0.1. 0.005 is less than 0.1. So education and experience are good predictors or kind of have a significant relationship with hourly wage. But gender and age, not really that close, right? I mean, I guess maybe gender is a little bit closer, right? So even though I did find evidence that looked like maybe there was some discrimination going on, I couldn't say that there was any effect of gender at the 90% level, right? Because I couldn't reject the null. Excuse me. So what? It was just education experience there. Okay. Any questions on that? Yeah. Yeah, so I haven't went over that, but. Yes, from this Excel output, and I make, depending on the size of the exam, I might sometimes cut this off, so I wouldn't rely on those. I really want you to rely on kind of using those p values. But yeah, actually these confidence intervals. And the problem is these confidence intervals will always only be for one level, right? I've got 95%. So if I ask you for the 99, you might not be really sure, right? That's why it's going to default to using that p value. But yeah, it does give you these confidence intervals, and essentially these are confidence intervals for what that coefficient is. So the confidence interval, kind of like when we're doing two populations, if it doesn't cross over 0, we can actually say there's an effect, right? If it does cross over 0 here, oh, that means the coefficient could be negative, it could be positive, I don't know. Yeah, you could use those confidence intervals. In practice, we more rely on those p-values just because you can actually play around with things and you can get 2, but you can never get all 3 at the same time. So it's just more relying on those p-values. Questions on that? We'll keep moving. Okay, so let me think. I want to outline this for you. I think I did this for my last class. I think this is just you're studying these regression practice exam questions. Also, following Friday, I'll put the answer key up to the 5th and 4th Excel. So that 5th Excel, even though it isn't Excel, it's a lot of the stuff that kind of questions I could ask you to do if I just gave you the output. That was really the only part you did in Excel is find the regression output and then answer the questions. So you'll have that answer key, some additional kind of go back through, and depending, even if you did well on that, if you didn't do it at all, make sure you look at that answer key. It's another going to be a good practice or another kind of good study material. But the things that I'll expect you to know when it comes to linear regression. So 1, you need to be able to interpret slope coefficients, right? Where we said that's a 1 unit change in X, changes our predicted Y value by whatever that slope coefficient is. You need to be able to interpret intercepts. We said that's what? Predicted Y value when all of our X variables are equal to 0. Yep. So you're gonna have to know how to interpret those from different kind of examples. Excuse me. Sorry. You can drink water. Oh, I choked them. All right. Excuse me. Okay. So, next thing is you need to know how to calculate test statistics. That should be as simple as taking that coefficient, dividing by the standard error. Next thing, know which variables you can say have a significant relationship. Those will be the variables for which you can reject the null, because the null is always starting out assuming those slopes are equal to 0, or that there is no relationship. So if I can reject that with a low p-value, right, when the p-value is less than alpha, I'm saying that I found evidence of the relationship. I can reject that there's no relationship. So know how to make those rejection decisions, determine which variables have a significant relationship with that y variable. Okay. So we got 4 things kind of out of the way there. 5th thing, know how to interpret that r squared, and also know kind of how adding in additional controls should increase that r squared. Okay. Oh, last thing, I already went through it, but how do I make predictions, right? So know how to make predictions using these coefficients for a hypothetical person, right? And I give you what that hypothetical person's X values are. I'll be very explicit in like exactly 12 years of education, 4 years of experience, right? 30 years old, whatever the example is. Okay. So know how to make those predictions well. Those are like all the kinds of questions I would ask you on linear regression stuff. I'll likely kind of give you 2 different kind of sets of output and then ask you several questions off that. I might maybe got these. I can't remember if I did 2 or 3, but no, I did 2. The other one I kind of set something up more similar to what we're going to go through now. But yeah, 2 different kind of Excel outputs, and then be able to answer any one of those. What did I do? 1, 2, 3, 4, 5 things. How do we know what's 1 and what's 0? Yeah, so on this one, it outlines it kind of right here. So I, on the exam, probably be a little bit nicer here, and I wouldn't just call it the gender, I'd probably call it male, right? So usually the name of the variable is like, that's when it's a 1 and then 0 if not. Spoiler alert, I'm doing one of the examples when you're here, so this is a benefit of coming to the class. So one of the regressions I'll use is looking at, I believe it is crime data. But one of the variables on the right-hand side is whether or not it's a red state. So the variable literally is red state. When I say red state, did they vote Republican and then 0 if not, right? So red state is a 1 if the state voted Republican, 0 if not, right? Or here I would make it variable male, so 1 if male, 0 if not. Other questions on that? Does that make sense? Yeah.
For the interpretation of the coefficient,
Mhm.
on the practice exam, there's like multiple choice ones and then there's free response ones. Is it gonna be multiple choice?
Yeah, so the final, I'll make all multiple choice. Those short answer ones, like if you can, I think it's valuable in trying to be able to write that out on your own. And so that's why I kind of had some of that more free response. But you know, if you can do the free response, you should be more than okay then when it comes to me giving you just 4 options. Like for instance, this education one, right? We said it was 1 more year of education, increase my predicted hourly wage by $1.23, holding everything else constant. You know, so if I'm looking at these, if I can write that free response, right? None of these even really remotely make sense except for C, right? Which is what I would have written out if I didn't have any options. Does that make sense? Yeah. Any other questions before we keep moving here? So that would be everything for the linear regression stuff. Oh, I'll save this. I'll save this one. Well, 15 minutes. Well, we can kind of focus on older stuff next class. So let's say I had an example like this. So I would probably write out, I might explain kind of a regression, and then I would think it's probably a good thing to write it out to be able to have a nice visual. So here, I want to estimate the relationship between child's birth weight and a mother's age, right? Where my birth weight is the dependent variable. So right away, I would write out what I'm looking at, right? So I'm trying to predict birth weights using kind of the mother's age, right? So that's my regression equation, right? And they're going to go back and say, okay, they found the intercept coefficient was 3,524, right? So how would I interpret that, right? So 3,524, don't know what the slope coefficient is yet, but it doesn't matter, right? Because how would I interpret the intercept here?
Mother's 0.
Yeah, if the mother was 0 years old, the expected birth weight is 3,524. So this is where the interpretations of the intercept will be very weird sometimes, right? No one who is 0 years old is having a child, but that line starts somewhere, right? So just because we don't see data down there doesn't mean that the line doesn't have to start somewhere, right? Mathematically. So that would be how we interpret the intercept. So where is it? The expected birth weight for a mother who's 0, 3,524. I don't know, I probably could have asked some more questions here. So let's say that we've got a slope coefficient of 2.54, and you know the research includes that as a mother gets older, children have a higher birth weight, right? So what's wrong with this logic, right? Well, first of all, it's not a question, but if we think about that slope is 2.54, what I'm really saying is the interpretation of that slope coefficient is for every 1 unit increase in X, so for every additional year the mother is in age, we would predict birth weights go up by 2.54 grams. Right? I believe it was grams we had to measure. Now, why can't I then make statements like, well, then it's better for mothers to be older when they're having kids? Because I think hopefully you know inherently like that's not true. That's actually the opposite effect. But why might I be seeing a positive effect here? Well, I need to remember, and I might ask, this would be a really easy question in the exam if I ask like, what's wrong with the logic of making these causal interpretations? We are only finding evidence of a correlation between these two variables, right? And it's likely that we've omitted a lot of other important variables that are going to be biasing that slope coefficient or biasing that correlation that we found. If we don't include a lot of other variables that matter, things that might be correlated with the mother's age, like the fact that the older you get, you're more likely to have a higher number of years of education. You're more likely to have a higher income level, right? You're more likely to be responsible. Like all these things that we can't control for, we're going to be kind of biasing that effect of the mother's age if we just have that naive regression. So anytime we have these results, we need to be a little bit cautious because it's just evidence of correlation. So, any questions on that before we keep moving here? I might also give you something like this, a little bit different format. I might tell you the intercept, I might tell you the slope coefficient, and then ask you to make a prediction for a mother who is, I don't know, 30 years old. It's simply plug in your intercept and your coefficient value, and then plug in that hypothetical kind of X value or mother's age here. That should be hopefully an easy one, right? If I'm giving you that slope and intercept coefficient, and then asking you to make a prediction from a simple naive linear regression like this without additional, right, kind of several variables on the right-hand side, making those predictions becomes a lot easier, right? Questions on that before we keep moving? So, I'm going to go back here a bit. So this first kind of question is talking about what type of distributions that we use, and we're going to have different types of problems. So I want to kind of outline it here for you. We won't get through a lot of it today. We'll pick up and try to do a lot more hypothesis testing stuff on Friday, but we had a couple different scenarios. So one, we were looking at the difference in sample means, and somehow we were given known population variances, right? We also had examples where we were looking at the difference in sample proportions. These were the two scenarios where we said we get to use that standard normal distribution or the Z tables, right? So anytime I know the population variances, and I'll use the notation, I'll show you when we go back to the practice exam, I'll try to not only say here's the population variance, I will give you the notation, you can kind of tell what type of example you have, right? So if you know the population variance or we're dealing with proportions, always use those Z tables. Our other scenarios were, I'm looking at the difference in sample means, but all I have are sample variances. I'm looking at a matched pairs example. So I have this difference variable. Usually this is like one population before and after. I create the difference variable, then find the average of that difference variable and the variance of that difference variable. These were going to be scenarios where we use those student T distributions or the T tables, right? So anytime you have a matched pairs, kind of the sample difference example or difference in sample means with sample variances. Now we weren't going through it by hand, but technically, we also are using that student T distribution when we're looking at coefficients. So the standard error, I said, remember, was kind of like the standard deviation or like the variance in that coefficient. And so these are all examples where we could use that student T distribution. So notice here, for these coefficients, you will always have a two-tailed test coming from a student T distribution. So that kind of might help keep track of things. Now, if I look at like this problem here, notice I use the notation. I tell you that here we've got sample variances. Okay. So if you go to your formula sheet, just kind of walking through that, it also tries to remind you, if you've got sample means and you know the population variances, use the Z table, right? Here's my confidence interval. Here's my test statistic. Difference in sample proportion. Here's my confidence interval. Here's my test statistic. Oh yeah, it reminds me, use that Z table, right? Standard normal distribution. Now, if I only have the sample means and I only have sample variances, which is what that problem kind of outlined, right? Here's my confidence interval, test statistical equations. It reminds me I'm using the student T distributions. And my degrees of freedom is this nasty equation, which I said I'm not going to make you use. So even though it's up there, I'll kind of show you. I can give you an assumed true degrees of freedom. Okay. Then down here, we've got kind of our matched pairs examples. So confidence interval, test statistic for that sample difference. Here, you don't need all these equations on the right-hand side. This is really me doing overkill because I'm not going to ever make you calculate the slopes. I'm only going to give you what Excel has already calculated for us, right? But these are the equations that Excel is using. You could make simple predictions. We kind of walked through an example just previously of doing that, right? We had one X variable. Once we have the intercept and the slope coefficient, we can make predictions for our Y variable. Test statistic for these coefficients. And then here, making predictions with several variables. And then you're not going to have to calculate the R squared. All you have to know is kind of how to interpret it, knowing that adding in more controls is going to increase that R squared. Any questions on this before we keep moving here? Okay. So, I think kind of hopefully having these formulas, trying to kind of at the very least match up the notation. It's harder to kind of pick the wrong ones. Right? Where are we at on time? Okay, we probably have enough time to get through this one. So let's say I found these two sample means and I only have sample variances and I've got two different sample sizes. So I've got 28, and I'll show you what I'm writing down in a second. I just want to make sure I get all these numbers right. 16 and 9, 40 and 50. Okay. So if I wanted to build a 95% confidence interval for what the difference is between Indiana and Ohio's BMI, right? And assume that the degrees of freedom is 50. So what would my alpha value be here at the 95% confidence interval? Yeah, 0.05, right? So I go to my formula sheet. I've got the difference in sample means, and I only have sample variances. Here's my equation, right? So all I'm going to do is start plugging in what I know, right? So here, I've got my two sample means. I then take each group's sample variance over its sample size. The last thing I need to do is look up this t-value. And looking up this t-value for confidence intervals is very similar to when we did critical values for a two-tailed test, right? So we're looking for that t-value that gives us alpha total outside of our confidence interval, or half of alpha on each side, right? So if we add the 90, I think it was 95%, half of alpha here is what? 0.025. So I want 0.025 in each tail. My degrees of freedom, I was told that was calculated for me, was 50, right? So I go to my student t-table. I want the area of 0.025, degrees of freedom of 50, 2.009, right? So that was the last thing I needed. Now it's just a matter of getting comfortable, getting used to kind of getting these entered in my calculator correctly. Now, if I'm looking at this, I know that my confidence interval has to be based around what value? Yeah, whatever this sample difference is, or -1. Okay. So if I'm looking at my options, where's it at? There we go. Can I rule any of these out? So it looks like -1, unfortunately, is in all of these. However, if I'm looking at like this one, -1 is a lot closer to -1.48 than it is to +1.48. So it has to be smack dab. No, I can actually rule this one out. I don't think any of the other ones I can't, right? But sometimes I'm going to give you these where maybe I even made this one so that it was only like positive values, right? So you can maybe rule some of these out even if you don't need to calculate. Now, you're never going to be able to rule it out all the way down to one answer, right? But you can maybe eliminate some of the other ones, right? But from here, it's just a matter of, like I said, getting that entered in your calculator correctly. I don't know the values off the top of my head. I don't have my calculator out. I'll make sure I bring that next class so we can kind of line this up. I mean, you got the answer keys up there, so we'll let you know what those values could be. We've got it all set up. Like I said, a lot of this is going to be making sure, even if you don't know how to set up, if you can get it set up correctly, making sure you can get this entered into your calculator correctly. Okay. Questions for me before we get out of here? Okay. I also may be getting up an additional practice exam, just more questions, just to give you more practice if you want it. So you might see that pop up there on Canvas this afternoon. Other than that, so I did mention that we won't be doing that review on Monday, so you kind of have like finals week off to study. I will be available Tuesday most of the day, so if you're wanting to stop by, just shoot me an email and I'll make sure that I'm physically in my office. Otherwise, I'll be around the building most of the day. Okay. Questions? All right. I will see you guys on